Good morning, everyone. Now, as far as I remember, that we are going to start a new topic. Well, it's not a topic, not a chapter. We are still in memory management. And in the last class, we came to the end of the bunch of algorithms that we discussed, isn't it? If you can still remember all those algorithms, very important. I'm waiting for my computer to get started. It does take a lot of time, especially after a weekend. It's just really getting worse and worse. But uh, in the meantime, do you have any questions? If you have any questions related to what we studied, and again, I got a few emails from one or two of you asking me to share the slides that I'm using here, but I'm not going to share it because the problem is that if I share, the students will only read these ones. In fact, that's not the right thing to do. As a student, you're advised to study uh, the slides, the study slides. And as I mentioned right at the beginning, that all the materials that you see on my slides, they have been copy pasted from the old slides, old study slides, which are available for you on LMS. Everything. Because over there, you will see when you go to those slides, it's pretty cluttered. That means they have given a lot of other information. And they have said those things and try to explain those things in different ways, using different vocabularies. And sometimes it's pretty confusing. And especially so if you use those slides for the teaching purpose, that doesn't really work. But that's one of the reasons years ago I made these my own teaching slides. If you don't find any information, any of those information right there, and you must immediately let me know. Okay. So the point that we have to go to Google Meet. Google Meet. This is the one. I see today it's a little bit slow. Seems it's very slow. So what we are going to study today is page designing issues. There are three things or four things that we are going to pass through in this particular week. It's all related to memory management. The things that we studied in the last class, you will have to keep them in the perspective. You will have to remember all those things if we want to move forward with these new lessons, new parts of lessons. Wait a minute, we are in the middle of that. is kind of hanging, not responding. Anyway, we'll sort it out. It may take a little bit of time. So the things that we are going to study, the things I was talking about. The first one is page implementation issues, that's page design. Once we get past that, then we'll be studying the page designing issues. Page implementation issues, page design issues. Maybe we'll start with page designing issues first. And then we'll be studying that's an important part towards the end. The role of operating system in this virtual management or in handling these page faults. That's what we are going to study. And finally, we will talk a little bit about segmentation. So these are some of the things that we are going to study. So we will have to pay attention to that particular thing. It is taking an enormous time. Internet is really bad today. Yes, here we are. Let's come up. Let me share with you. See, everything is getting stuck somewhere in here. Okay, at least now you can fiber. Now you can see the screen. And let me see how much time it takes for it to wake up. So in the meantime, just don't forget the things that we already studied, the algorithms especially, and the conversion. Well, it's not exactly a conversion, it's actually a mapping, as we understand. Then memory management, that is what we study. The MMU's job is to map it properly. And that's what it does. So we'll be looking at, we'll start with designing issues. That's my intention. Let me see why. Page implementation issues, page designing issues. Let's get started with the designing issues, okay? And then we will talk about page implementation issues later. So the next 2 days, we'll be focusing on these two. Page designing issues. Well, again, do a quick review about most of the important things that you'll be needing to remember. But remember, this, if you want to follow these parts logically, you want to understand, you must remember the things that you've already studied in the last part, in the first part, basically, in the first part of memory management. All right? Oh, it keeps heavy. What is this? It's unnecessary windows. Why it doesn't come? Okay, at last. So here we are in page designing issues, and designing issues is one of the most important things that we will have to remember. We'll have to study. What do you mean by designing issues? Designing issues literally means, well, why it is important in the first place. Designing issues are important because okay, the designing issues that we are going to study is designing. Why these designing issues are important? These designing issues are important because remember, page is a logical concept. Okay, let's not, don't forget that basically that was the fundamental idea. Your program has now already got its address space from CPU, and a chunk of its address space is what we call the virtual address space. Well, a chunk of virtual addresses basically. In between these are the virtual addresses, and this is what we call VP or virtual page. So we had virtual page. Uh, we, we have virtual page, and we have the virtual the paging. That is what we call it. Sometimes we use the word virtual, sometimes we don't use the word virtual, but whatever it is, that's what it is. Now, how will you design the virtual page? In other words, what will be the difference and what should be the size? So that is what will be the most important. The design issues for paging system, the local versus global allocation policies. These are important issues related to page design. Basically, we have to remember a bunch of theories here, but sometimes it's not exactly any algorithm we are going to find in this part, but these are important concepts. So let's see what is local versus global. Now, local versus global is easy to understand. You have to take a decision whether to remove when it comes to the page removal. That means when there's a page fault, remember we get page fault, and on top of that, the RAM is full. RAM is full. So if the two things happen together, then we have to go back to these bunch of algorithms that you were looking at, right? FIFO, LRU, WSBlock, and etc. To decide on how to evict one of the pages to make room for another page. Now, if we want to do that, then of course we have these bunch of algorithms right here. Now, there's more than that, what you can see. But there should be a policy. Remember, this is not an algorithm as such, but this is more of a policy. Now, policy means will you go for all the programs? Say, for example, you are talking about FIFO. Keep it simple, FIFO. First in, first out. So will you apply it for all pages or all pages coming from all programs? Because people say the oldest one must be evicted. Now, what do you mean the oldest one? Oldest one doesn't mean considering any program or for any program or any process, or just the current one? This is the question. Okay. If you only go for the current one, then you are doing something locally. If you are going for all programs, if you consider the oldest page among all the pages that we have for all the programs, then definitely you are going for the local one, for the global. So you have to decide whether you want to do it globally or locally. An example, but this piece of information that I have underlined right here is important for your exam. Some page replacement algorithms can work with both policies like FIFO and LRE, but some work only with the local policy. It's quite obvious because when you make a WS clock, and if you remember that workings is a bunch of pages that always go hand in hand. Now, how can they come from other programs? Well, they must be from the same program. So WS clock, the same program. WS clock must work with a working set of the same program, working set of pages, the same. You get an example right here. As you can see right here, we A6 causes page fault, and this one will be the local one, and this one will be the global one. Here is A6. We put in A6 by replacing a page. Supposedly, it's a oldest page of program B. But here we replaced one of its own pages because the program A was creating the fault. Okay. A6 stands for program A causes page fault. Is local, is global. Okay. So it's pretty easy to understand. It's not difficult at all. Think about this one. And what do you think? Which page is replaced using the local part? Assume that it is always the last page. But if you apply global policy, which page is replaced using the global policy? Assume that the replaced page is always applied, the process taking most pages. In that case, a good candidate is A7. Think about it. It's a question sometimes you might get in your exam. Common questions. Load control. What is load control? That's another issue. Remember, we are in page designing issues. When the combined working sets of the process exceeds the capacity of memory, no way to give more memory to those processes needing it without hurting some other processes. The combined working sets, the situation that we define here, combined working sets of all processes exceed the capacity of memory. So basically, what happens that if you put a working sets of all of them and they run out of space, that they also want to run, basically you run out of space because you were trying to implement working set or the working set model. In fact, working sets, that is the problem. That is where what we're talking about. In fact, it's the same thing that we talked about, if you can remember, in the previous class. Because a working set, as I mentioned over there, and I repeat, working set is a good bit of technology, a good bit of algorithmic interpretation. Okay, because working set takes into account several pages together. For example, working set may contain P1, then P5, then P4, 10, and P11. Okay. So all these pages group together because every time one of these pages, say for example P1 is referenced, then we know this P1 to execute its code will be needing the supports of these other pages. Okay, it's all about a part of the algorithm. You can't just say that they're always going hand in hand, but it's the usual trend that OS has observed. So OS makes an inference from that, and they put all of them in one cluster, which is called a working set. Now, once you have a working set in place, this is the most important thing. Now, imagine that you can only replace one working set by another working set. And as I said, why we have the load control issue here is because the CPU made a fault, and the fault for page one. But OS tries to bring in a whole bunch of pages. Okay, so that is where the load control issue comes into play. There was a request for one single page, but operating system wants to bring in a whole package of pages because it knows that this particular process behaves in such a way whenever the codes inside process one are executed, process one, page one executed, page one, page three, page four, page 10, page 11 will be needed subsequently. All right, so this is the deal right here, and that is where we get the load control issue. So how may I address this load control issue? So what is the load control issue basically? Basically, the problem is that very soon you will see there is no space in RAM. So the system will go for thrashing, which, as I said, it's not good news for your system, for your computer in general. So that to avoid thrashing, what it can do, we applied, if you can still remember, something called working set model. Working set model. Because now it's not about asking for one page, because up to working set, we were sticking to demand paging. If you still remember these words we discussed, demand paging. That means paging based on demand. Or in other words, a paging, you do paging, that means bringing in or shuffling those pages and bringing in the other pages and evicting some of the older pages. You do it only after you get a fault. So everything was essentially dependent on fault. Try to understand that part. Okay, everything was dependent on fault. Now, that's what we call demand paging. But now, from demand paging, we are moving to pre-paging. It's a very important word. Pre-paging. Pre-paging means once you have a steady WS-based model, working set-based model, that's what we call model, then we know exactly which working set of pages will be required after which working set of pages for a particular process, for all the processes. So what we do, rather than waiting for a fault to happen, in this case, of course, the fault will happen from a working set and must be replaced by another working set. So that means when the fault happens, you will have to clear up a 5 or 10, depending on how many pages are there inside a working set. It's a 5 or 10 page frame, which is quite tough on demand to clear it up. But rather than doing so, if we can do it a little earlier, at the time when the demand has not yet been created, that means we still have a little bit of time. So what do we do from time to time? This is a periodic operation. Periodically, at a regular interval, you keep the page fault rate acceptable that take into account the degree of multi-programming, and you consider not only the process size, process rates, but also its characteristics, CPU, IO-bound process. Just a handful. These are not algorithms, but these factors we take into account. And what do we do? To reduce the number of processes competing from memory is to swap out some processes and free up all the pages they are holding, to divide those pages up to thrashing processes. So basically, from time to time, you check the memory and you clean up. It's basically load control is all about periodic cleanup. Okay, that we do by using a two-handed clock. They didn't mention it right here, but we will find it very soon. The double-handed clock. You got a one-handed clock, and now we will have two-handed clock. Okay. So how about the page size? So what should be the page size then? That is our next important issue. Yes. What is going to be with the page size? It's often the parameter. Now, when we talk about page size, bitmap size, there is always a kind of the controversy. You have to take a decision. You have to take an educated decision on that. The page size is often the parameter that can be chosen by the operating system. Determine the best page size requires balancing several competing factors. There's no overall optimum. Now again, whenever these issues come up, and they do come up quite often, there are arguments for small size and arguments for large size. So the point is often the parameter that can be chosen. Determining the best page size requires balancing several competing factors, and there is no overall optimum. The arguments for small size and the arguments for the big size. Like what should be the large size and what should be the small size? For the small size, the word that will keep chasing you is fragmentation, because the page size is too small. So basically, you're making lots of fragments. But that's the argument for the small size. An internal fragmentation, and in many pages. And the page table is large and transferring takes more time. On the other hand, if you have large size, the common one use page to memory than a small size. So there's always this kind of arguments. So a reasonable compromise, perhaps, is this one. Reasonable compromise, they never ask you to do these calculations, but if they do, just remember this formula. That should be enough. This one will be enough. Because there is literally no overall optimum for the page size. This is going to be an important separate structure and database. In fact, this is the beginning of a new era in this concept. Try to understand a little bit. So far, we were taking the entire program and paging it out, right? But as you said, that we know that program, when it is converted into process, it is split up at least in two parts. That was something that we referred to earlier as the very basic implementation of segmentation that the OS does. Even if you don't apply segmentation, all processes, when they get loaded, they get segmented in that way, at least the three parts, the code part, the stack part, and the data. And that's exactly, so we had a data part and we had a different part. So everything was part of it, like a data part, and then we had, for a program, we have the code part. It's a code part and the data part. I imagine that now, of course, everything is not loaded in a contiguous space. So it's a program, has a whole bunch of spaces there, a whole bunch of pages there. So previously, if you apply page up to this point, if you apply paging, you'll end up with one page table. Right. But now, by separating the structure of the data space, that basically that means the same program. This is the old program. This is the program one. Now it is represented as this and this. Both of them together become program one. Why? This is the data space or D space, data space, and this is a code space, or sometimes called the I space. That's because the instruction space. So we break it down into instruction space and data space, and each of them will be paged separately. So now for a page table, which is actually, we are moving towards segmentation. Later, of course, towards the end, the absolute end of this chapter, we'll talk about segmentation. So you will see we'll be doing the same thing, and we'll actually implement the same technique, segmentation and paging together. So that's it. That's what we get. So we have page, and we also have this one. Okay. And once we have this little part, then we understand how we are going to play them. Now what happens? So since you have separated both of them, the likely scenario is that on RAM, if this is the RAM, this is, say, for example, the data space, and this is the I space of the same program. Right. So some of the pages will be loaded on RAM. But to support these few lines of codes, you need to put a related data page as well. Because if the data page is available, these codes will not run. Right? So how do you keep track of which page, which page from the I space and D space match with each other? So you can't just bring in any, because you have to keep track of it. And for that, we use a linker. There we are. That is the most important thing right here. The linker and the hardware must know when separate spaces are being used. Both address spaces can be paged independent. In fact, they are both given separate address space, 0 to M, 0 to M. So now a program up to this point was having just one address space, and now they will be having multiple address spaces, at least two address spaces. Literally, later we will see even more than that. And each address space or each part will be done in a separate way that will be segmented. It will be paged. First segmentation, then the paging. All right, so that is exactly what we are looking at. And this is a new idea, new concept, very effective. And in fact, you will see, as I said, that it was the beginning of a new era, because this technique will make things absolutely flexible. And very soon we will move on to shared pages. And there we will see what we are doing, if we are talking about. So that is what we are looking at. If you move on to the next one, the shared page. Now, take a minute to understand that how important this little thing is. This little thing is very important because when it comes to sharing the page, it is important that we get it and we do it in a way that it tends to become a kind of solver, if I may use the word. Now, I use the word solver because that is what it is going to be. That is possible only because we apply this fantastic logic. Now, what is that? So think about it. Now we understand that we have split it up into two parts, right? We have split up into two parts. So naturally, if there are two programs, okay, two programs, this is program one and this is program two, and they share the same data part, but different code parts. Or they share the same code part, but different data parts. What does it mean? That means now we don't have to load them multiple times. For example, the code's the same, but codes are same, but data separate. Okay. Now, this separation between the codes and data makes it possible to to create a collaborative environment among processes. To understand what is going on, there's a program. There are two programs. Okay, program 1, program 2. Both of them, they are supposed to have I space and D space. I space and D space. This is the I space and this is the D space. This is the I space and this is the D space. Right? So far, they were individually linked by using a linker. That's what we are talking about when that program is running, that any part of this code, any part of these codes were loaded on RAM. So naturally, the relevant data page should be loaded there as well. That's what we are doing. But now think of it that a part of these is common. So what does it mean? That means that these pages shouldn't be repeated on RAM. I can put it only one time. And to support these codes, we have the data pages, the relevant data pages. The relevant data pages will be repeated. So one data page will belong to program 1 and the other one for program 2. But the I space only one time. Why? Because it's a shared code. Take a minute to understand. A shared code. So there is absolutely no point to repeat and to load the same bunch of codes 2 times on RAM. Because program 1 and program 2 are sharing the same codes. Not entirely, but mostly. So what you create here, you are starting to create something that we call an environment. Or you can better share a collaborative or shared environment for all the programs that to a certain extent use each other's code. Because by doing that, you can actually keep just one bunch of code on RAM and let them play, and anyone use it whenever they want to. Isn't that an efficient use of RAM? Indeed, it is. So we understand this little part and we go to the next level. What we do is a copy and write strategy. Now, copy and write, I mentioned for the case of the shared pages. In case of parent and child process, they copy it and put it right in the server. Okay. So basically, what they do is because this is now we have a common shared page. So if you want to share those pages, then you'd rather make a copy of it and give it to multiple users. They will be using it and they will return those data. In fact, if you go and copy the shared pages, you can start using only the page that are modified by either processes are copied. Non-modified pages may be shared by the parent and the child. This solution is applied always using duplicating process strategies. So basically, this is what happens when you are running programs on server. Because remember, number of processes, P1, P2, P3. The two will be asking for a particular data. So if you go along that way, you are basically not only sharing the codes, but you are sharing the data as well. Okay? And there's two slightly different ways of thinking. All right. And in a minute, I'll tell you what exactly it means and how do they do it. Think about your Google server or Google Drive. Remember, Google Drive itself is a storage. I might say the Google Apps. I mean, the Google Doc, Google Sheet, like a Google Presentation. So these are the most commonly used Google Apps. But what happens there? So basically, a program is a bunch of codes are running here. Okay, that means, say for example, Google Doc. Do you think that there are 1 million copies of Google Doc running on their server, running on their RAM at that moment? No. Only one line of codes. But these codes will be used separately or differently in a different way by 1 million Google users at the same time. You are using Google Doc at this very moment, I'm using Google Doc, and someone else is using Google Doc or Google Sheet. So what are we getting? The moment you want to access it, we get a local data, local database. That is what we get. Our own data are generated inside our own drive, and they will be stored. But for these particular codes, because we are not going to use them at the same point of time, but in a different way, we will get a separate copy of it. And we will use those codes to generate our own data part. And then everything, as you know, in Google Doc, Google Drive, everything is auto-saved. That means everything, the data that you generated will get auto-saved in your drive. So basically, they are giving you a copy of the instructions, and the data part is already there in your drive in a local way, and you are running them on your server and storing it inside your drive. Remember, nothing is happening on your computer. Everything is happening on Google's computer. You save on Google Drive. The Google Drive doesn't exist on your computer. It exists on the Google server. The key benefit of shared file is right here. That is one of the things that we discussed. The other benefit, as I said, was what we call DLL, Dynamic Linked Library. Okay, so what is Dynamic Linked Library? Must be another one, shared DLLs. Dynamic Linked Libraries. Must have known about Dynamic Linked Libraries. If not, then if you go to System 32 folder, okay, in your Windows environment, you'll see a whole bunch of .dll files. In our times, we used to joke that you just go there and grab some of these DLLs and delete them, and some of your apps will crash. It's so easy to crash your Microsoft. Again, Microsoft OS. But anyway, don't do it. So the point is that one of these .dll files, it's called a library file, but it maintains a dynamic link. So essentially, to keep it simple, it is a file. It's actually a program file, but it is not loaded like any other program file in its entirety on the RAM. So basically, we end up having a bunch of codes, bunch of shared codes. Remember, we just were talking about the shared codes. This bunch of shared codes, yeah, are pretty isolated and kept on the hard disk. So we keep it on the hard disk. We keep it on the hard disk. And we're not exactly loading them all the time on RAM, because over there, if you remember what we did right here, okay, we were sharing these code. Now, how about not keeping it right here? How about not keeping it right here? And we stored these files into 5 different files, or in one single file, and keep it somewhere on the hard disk until there's a demand. That is exactly what we are doing. Now, on your RAM, some other parts are running. And as some other parts are running, it might be program from program 1, program 2, whichever, because they're all shared. This is the shared code. We might actually say these are shared code. Yes, this is shared code. Now, each part of the program might be interested to access them separately. When they want to refer to any of these functions, those will be loaded on demand. Only those functions will be loaded and run. So basically now, each program is dependent on using a whole bunch of codes, which are shared resource, but not stored and not dumped on RAM during the runtime. These codes are being accessed straight from another kind of program file that is called DLL files. DLL files. Okay. This was first introduced by Microsoft, and with it came the environment. Now you understand what we are talking about. And Windows environment. That's what we are talking about these days, don't we? We don't say only a window. We say it's a Windows environment. Windows environment. So what we mean by Windows environment? Well, by saying environment literally means, think about this. Now you open your what do you call Microsoft Word, Microsoft Excel, and Microsoft PowerPoint side by side. And look, you just take a quick look at the top toolbar. How much of it are actually common? How much of it are actually common? So that is exactly what we were doing. We created an environment where they could actually play. So they could actually play. A program linked with shared libraries instead of including an actual function or the link. So what is inside these shared libraries or DLL files? Inside these DLL files, that is what we mean by dynamic linked libraries. So basically, if you look into it in a more careful way, what we essentially do is creating, sharing these pages. In fact, now, as I said, in your Microsoft environment, if you look at it and you will see that how much of the shared codes they're using. All these programs, whether they are there's the save button, and how many In fact, they have I should say, the 80% of their codes are shared. Okay, so what we use is Windows environment and Office environment. So Windows environment and Office environment. So these are the two things that we always rely on. So these little things are very important, key to the success of Microsoft these days, because they basically use the RAM in a more effective way. So literally free up the space. The library, all these functions, these library files, DLL files are essentially a bunch of stored functions, nothing more than that. A bunch of stored functions. And these bunch of stored functions are staying in one part. So what we have, the bunch of stored functions is whenever any of them needs to be referenced, if you go to an external link that I have used there, and probably you can try to open it, never the okay, it opened. It basically gives you a quick, it's an external link, of course. It tells you in short how exactly it happens. It's just a quick reference, good to know. Let's see how it works. How do the files work? Imagine two distinct files, example.exe, a common executable file, and the library.dll, a DLL that is used by the executable. Okay. How are those files connected by the operating system when example.exe runs? When example.exe runs, the operating system loads it and finds a table of data within it stating that this program uses the following list of functions from the DLL file library.dll, now which is technically called imports or imported functions from the DLL library.dll in the program example.exe. Then the loader code searches for library.dll, and if it finds it, the file is loaded. Inside this DLL file, there is another list called export list, which connects specific addresses to each of the functions inside the DLL file. From this point on, when example.exe needs to call a function from library.dll, it simply uses that particular address. So there you are. The first time any app in the Microsoft environment you have just installed and you are Some small English problem going on with this. Okay, back to where we are. So we understand that exactly what it is and how it works. Let's move back to focus on this little part. So we understand what it is and how it benefits. So we'll not move too much forward this stage, but the most important thing is to understand how these things work. So what are the benefits? The benefits are even the heavyweight, the heaviest weight processes, the processes that are supposed to have lots of, like your Microsoft Office applications. They're getting bigger and bigger and bigger and bigger. But if you look deep down, you will see that although they are getting bigger and bigger, but they are not actually like that, because most of them are kind of lightweight. They're super lightweight when they are running. Why they're super lightweight? Because they're using a bunch of data files. Because as I say, 80% of the codes are shared. And not only shared, but they are kept in the DLL files. So the actual program size is very little that needs to be on the RAM. And when it's on the RAM, from the next time on, the first time, it has to load that particular file, DLL file. From the next time on, it will just pick up the function from that DLL file. And the DLL file will never get loaded in its entirety. And there are a whole bunch of DLL files right there. And that's how your Microsoft creates an environment. In fact, when they introduced this technique of DLL, we started hearing that word environment, an Office environment and Windows environment. And so that is what we have in right there. Okay. That's the benefit that we get. So we get Windows environment, and we also get this Office environment, and everything is now environment based. That brings us to the cleaning policies. I said that, remember just now, a few slides back, we were talking about the issue, one of the issues related to load control. And when we're talking about load control, we talk about a technique where by using this technique, we can periodically clean up the RAM, to make sure that there is no spam, no trashing, that our RAM doesn't run into trashing, our memory doesn't go for trashing. That literally means all of a sudden the huge demand on memory space rises and we just don't know where to go. So that is so that is the one that we are revisiting sort of right here. As we can see, when it comes to implementing the load control, we need to have a cleaning policy. And the cleaning policy is the writing to dash is a big hurry doesn't occur. So it means that we must do something periodically to clean it. And for that, we use a technique that is called the two-handed clocks, the double-handed clocks. And how do we use the double-handed clocks? We use the double-handed clocks in a very strategic way. We use the double-handed clocks look at this one, the picture is already there, and if I can erase it or not. No, it can't be erased. So the way it works is, remember the clock algorithm? The one hand checking R bit, the other hand checking the M bit.
Hey, sit down.
Yes.
I think we're out.
The R and the M bits. So basically, when the page fault happens, there was the hand pointing at the second hand. This is the second hand, the following hand, following the pointing to the R bit, and the first hand was following to the M bit of the previous page. So if you use this one, what is the M bit? M bit means modified bit. Modified, why modified? Because this must be one of the data pages. One of the data pages that have been written and overwritten. If it is found to be one all the time, it might be dirty. So it's a good candidate for eviction. Eviction means swap it out and put it in your swap area. Swap area inside your hard disk. That's what we do. And the R bit, we already know its algorithm. If it is found to be 0, it will be swapped out as well. If it is found to be 1, then it will be retained, but the 1 will be converted, will be changed to 0, and it will move on to the next part. Okay, so that is how it works. The paging daemon is used. Remember this one. A daemon is a common program that the name of the program that we always use. Now this daemon will be using again the paging daemon, and this paging daemon is a technique to clean up these things. That means the daemon will be sleeping most of the time. From time to time, the daemon will be waking up. And these daemon from time to time will try to access a piece of data, and its basic job is to move around and check what's happening inside the data spaces. What is happening inside the data spaces? That means if it finds some of the data spaces are overwritten or needs to be cleaned up, it will clean it up. So the whole concept of load control with a particular cleaning policy, that is what we're looking at right here, is to avoid crashing. To avoid running into an emergency situation where you need a lot of space, a chunk of space, not just one page frame, but multiple frames together, because you're applying the OS is applying the working set model. And before that situation arises, that OS would rather be very happy to load the other working sets to keep them ready on RAM. pre-paging. So pre-paging that we learned previously, working set model, load control, and cleaning policy, they all go hand in hand. Although we have discussed in these slides, they have discussed them separately, liquid here, liquid there, liquid over there. But conceptually, you should think of them all happening. They're related to each other, and each one is basically complementing or supporting the others. The working set model, working set clock, the load control, and these two-handed clocks. All these are happening together. Okay? And with one single purpose, to reduce the number of page faults and to reduce the chance of thrashing by using pre-paging. But if you use pre-paging, you need to clear up some pages, page frames first. And that's what the cleaning policy is all about. At least, when we went to load control, we saw that they're at least applying some sort of logic that when it goes to thrashing, the OS doesn't care about the logic of process size or whether it's CPU lock process or IPON process. They don't really take care. Our OS has no time to take care of these things. It will simply, as I say, thrashing is really that. It will simply grab a bunch of pages, important, unimportant, which process, no one cares. We just grab them and then dump them out. That is not good. So how about the implementation and segmentation issues? They're talking about implementation and segmentation issues, and this is another part that we are going to step in. And I reckon that we will not get into the implementation part today, and we will keep talking about it later, because in these issues we will talk about the OS involvement with paging and the page fault handling, the instruction backup, the locking pages in memory, backing up store, policy and mechanism, and finally segmentation. As things that I already mentioned. Okay. Those will be implementation issues. So we stick to, for this lecture, we stick to what we learned in designing issues. To give you a quick recap of the highlights, the things that we have learned. First, we talked about global policy and local policy. Right? Then we talked about load control. And I would rather put load control and cleaning policy together because they are interrelated. In cleaning policy, we learned about a demon program that spends much of his time doing nothing, but from time to time wakes up. It's only one job. It is to scan the entire RAM to see where there are pages which can be evicted to clean up the RAM from time to time. That's what the job does. And we usually implement it by using the two-handed clocks. Two-handed clock. The first hand is checking the modified bit. If it's found to be modified, it will be kicked out, like a swapped out rather, in a more recent term. And if it says that it has been modified, to just move on and check the next one, which will be retained. Whereas the reference to the second hand, the following hand, keeps checking the R beat of the page. If R beat is found to be 0, that means the less reference page as for eviction. If Yes. Wait a minute. There is a power failure. I don't know for how long it will continue. But I'm on the cell phone, so on the cell phone I can talk to you because I think you can hear me on the cell phone, right? Yes, there's a power failure all around. So the slides are not flipping, slides are gone. Anyway, so the things that I was talking about, since I can catch up with you online right here on with my 3G, 4G, the things are the things that we were talking about. These were the things, the load control. And then another important concept that we learned was the shared page. Okay, so shared page was a very important one because by separating the D structure or the data structure from the I structure, the I space, the D space, we could basically generate a lot of space. Okay, we could generate a lot of space, and a lot of space because we write the programs in such a way that they share each other's codes. So naturally, the shared codes don't need to be always on RAM, and they are stored in a separate program file. It's a different type of program file, which is called .dll. And it's also a program file, but it's loaded only the first time. And since then, you don't have to load them. All you have to do is, it's basically a stack of functions that you have. Okay. So that's all. And in the next class, we'll move into the segmentation issues and the implementation issue. First, the implementation issue, and then the segmentation issue. The segmentation, implementation issue can be a little bit more complex, but it's okay. That is important as well. So that is mostly about operating system's role in how to handle these page calls and paging issues. Okay, I can't take your attendance today, but later I will give all of you the attendance. It's okay? Because it's still power off right here. So catch up with you in the next class. And for today, all of you, you will get your attendance. All right? So that's all. And we will catch up again on Wednesday. But in the meantime, go ahead and give it a read. And if you have any problems, you're still encountering some problems with your lab, just give me an update on that. Okay, that's all. Bye, because I'm kind of like in the middle of darkness. I don't know, what am I going to do in the next class? See you. Bye.
Bye.